Okay, here we go with a quick implicit differentiation. I wrote reminder, review, whatever, because in the assignment for today where we have some more derivatives practice, there are a couple of implicit derivative problems. So I thought, hey, why not just introduce them now, right? Yay, thumbs up. So the general idea, let me actually just flip this over and then I'll come back, is that when we take the derivative and we have y equals 5x squared, and we just casually write y prime equals 10x, what we've really done is we've taken the derivative of both sides. The derivative of y we've written as y prime, and the derivative of 5x squared we've written as 10x. Well, this is a shorthand version that we've become accustomed to. What we're really doing, if I want to be really specific about it, is I'm taking the derivative of y with respect to x. So when I take the derivative of both sides, I'm taking the derivative of y with respect to x. And on the other side, I'm taking the derivative of this side with respect to x. So the derivative of 5x squared is 10x. And then I have to chain on the derivative of this inside thing. Well, the derivative of this inside thing is the derivative of x with respect to x. Well, dx is just a form of 1. I don't need to include it every time. So really all I have is dy dx equals 10x. Nothing really new or out of the ordinary for us. We just don't usually write dy dx because it's annoying. I hate writing this fraction when I have one line and it's just more, pen strokes and it's annoying, so we don't write it that way. But when we have a problem like over here, and I have xy equals 5, well, I have two choices. One choice is I could rewrite this. Okay, so I could rewrite this and solve this for y, and I could say y equals 5 over x. And then I have my x's and my y's separated, and I can take a derivative just like I normally would. I can say y prime equals, and if I were doing this, I would rewrite this as 5x to the negative first. I would not use quotient rule. If I have a simple fraction, I'm going to avoid quotient rule if I can. So my derivative is going to be negative 5x to the negative second, or negative 5 over x squared. So there's my derivative. Okay, but let's say instead of doing it traditionally, I go and I do it implicitly. So this would be called explicitly. This is the way, if I had a problem this simple, I probably wouldn't approach it implicitly unless I just wasn't really paying attention, because it's so easy to solve for y. But let's say I did it implicitly instead. So this means all of a sudden, I'm going to take the derivative of this left-hand side. So the derivative of the left-hand side is going to require product rule. It's a product. It's x times y. So I'm going to have to take that derivative using product rule. So I'm going to have the first term, which is x, times the derivative of the first. So that's the derivative of y with respect to x, plus the second term, which is y, times the derivative of the first. Well, what's the derivative of x? We would say it's 1, but I need to chain on the derivative of the inside. So I'm chaining on technically a dx. Well, I don't need to worry about that. I can just say this whole thing is 1, but technically that's what I'm doing. Every time I'm taking the derivative of an x, I am technically chaining on a dx. Just like when I take the derivative of a y, I'm chaining on a dy dx, or I'm saying the derivative of y is dy dx. So I continue, I have the equal sign, and the derivative of 5 is 0. So what I really have here is x times dy dx plus y equals 0. Well, if they asked me to find the derivative of y, this isn't the derivative yet. This is all mixed up still. So I need to solve for dy dx. So I'm going to subtract y from both sides. And then I'm going to divide both sides by x. So I'm going to move over here. So now dy dx equals negative y over x. Well, that's my answer. Well, you might say, how can what I got over here, I got negative 5 over x squared if I did it like a more traditional approach, and I got negative y over x here when I did it implicitly. These two should be the same, right? Like I took a derivative, this is y prime, this is dy dx, they're the same thing. They should be the same. Well, they are, you just have to go a little, if you were doing this problem implicitly, you can stop here. You are allowed to have y's in your answer when you take a derivative implicitly. But just to prove that these two things are the same, go back and use a little substitution. So how can I make sure these two things are the same? Well, let's take this y out and replace it with what y is. So negative y over x. Well, go back to the original. What does y equal? Y equals 5 over x, right? If I wanted to solve this for y. So let's put negative 5 over x all over x. When I have a fraction and a fraction, this denominator pops up there, so I have negative 5 over x squared. Boom. Same thing I have there. So it is the same. Oh, low battery. Hopefully you got all of that. Okay. Okay, so that is your general quick reminder of implicit differentiation. So let me go and try this one and show you how it doesn't get any more complicated really than examples 1 and 2. Even though in the circuit, it might get a little bit. I think she threw in some examples that are a little bit more difficult, but whatever. You can handle it. You can do it. Okay, so let's try it. You might want to pause the video and try it yourself, see if you can do it. If you remember what we're supposed to do, it looks a little different, but let me walk you through. So the derivative of x squared, we do the derivative just like normal. We go 2x, and since this variable is x, I don't need to chain on. Plus, the derivative of y squared is 2y, but I have to chain on. So every time I take a derivative of something that has a y, I need to multiply on or chain on the derivative of y with respect to x. I still hate writing dy dx, so I'm going to start writing y prime. I feel like the algebra is easier when I have it looking like that than when I had it looking like the dy dx. So I would recommend when you chain on, you make it a y prime. So 2x plus 2y times y prime equals the derivative of 3 is 0. I have to solve for y prime, so y prime is going to be take this to the other side, divide both sides by 2y, and there we go. Y prime equals negative x over y. And you can keep it just like that. All right, this one, let's take the derivative of both sides. So P.S., this example up here, you could solve this for y and then take the derivative, but you have to be a little bit crazy because first of all, when you solve this for y, you're going to be taking a square root. You would have a positive and negative result, so you'd have to take a derivative twice, and it's just a mess. So taking the derivative implicitly actually is like a simpler, more elegant approach than trying to solve this for y. Same thing here. I could technically solve this for y first. I'd have an arctan in the problem. In fact, now that I'm talking about it, it sounds like that would be fun to do. First, let's take it implicitly. So let's look at how maybe simple and elegant the math is here. So the derivative of the left side, derivative of tangent, is secant squared. So we're going to have the secant squared of y, chain on the derivative of y, equals the derivative of 2x is 2. So y prime is going to equal 2 over secant squared y. And really, can't we say, if you want to, this would be a perfectly fine answer. If we wanted to like just be fancy pants, then secant squared on the bottom would be the same thing as cosine. Right, so that answer would be correct as well. 1 over secant is the same as cosine. Right? Oh my God, did I just like do something really stupid? If secant's on the bottom, yeah, cosine. Yeah, good, okay. So now let's just go just for giggles and see what happens if we did it explicitly, traditionally. Let's see what happens when I solve for y first. So you might not even know how to solve for y. You might be like, Miss Dan, you crazy. I don't even know how to get that. So how to solve this for y would be to take the inverse tangent of both sides. So that's how I separate a tangent from y. This does not mean tan times y. This is the tangent of y. So to separate it, I would take the inverse tangent of both sides. So the inverse tangent of the tangent, well now this is just y. So y would equal the arctangent of 2x. Okay, so now let's take the derivative. Well, y prime is, we just went over derivatives of inverse trig. So we make a fraction, 1 over 1 plus this squared. times the derivative of this, or you can put that up top. So that's the derivative of y when I do it traditionally. How the heck are these two things equal? Well, that's going to involve some like serious algebra-ing, which I really brought myself into a direction that I don't want to go. It's kind of fun, actually. So I guess if I really wanted to manipulate this to show that it's the same, I would say, okay, what is x squared? So what is x? So x is the same thing as the tangent of y divided by 2. So I can replace x squared with tangent of y divided by 2 squared. I'm totally going to run out of room on this little thing. So this would become 2 over 1 plus, this is squared, so the 4 and the 2 squared will cancel, and I have tan squared. OMG, does anyone know what 1 plus tangent squared equals without knowing that I'm supposed to be getting that? It's one of those Pythagorean identity things, one of those Pythagorean triples. Remember from pre-cal, sine squared plus cosine squared equals 1. And then you have the ones that come from that. You've got 1 plus cotangent squared equals cosecant squared. And then we've got tan squared plus 1 equals secant squared. We'll go through them again when we have like, when it becomes more relevant, but there we go. 2 over 1 plus tan squared, that is secant squared. Oops, this is a y. Samesies. Amazing. Isn't math so cool? Okay, if you tuned out long ago, I understand. I'm gonna go post this and then you can start on the circuit. Have fun.